I wanted to give you an example other than the ones that are in the handout that I had you read through and the one we did in class. And I wanted to do it with a dot product that's not a usual dot product or an inner product that's not a usual inner product for us. So let's do another one of these with an integral inner product. So let's say we have the polynomial space. So polynomials of degree 3 or less along with the 0 vector. Or the 0 polynomial, so P3. And let's say we have the inner product of two polynomials here is the integral from 0 to 1 of the P times Q. So this example is asking us to convert the standard basis for P3, the 1x, x squared, x cubed, to an orthonormal basis. So to do this, we will use the Schmidt orthogonalization process and then normalize the vectors that we get. So again, remember, we form an orthogonal basis using the Schmidt process and then make an orthonormal basis by taking that orthogonal basis and just normalizing the vectors. So to do that in this case, remember for Schmidt, the first step is to say your first vector in the orthogonal basis is the very first basis vector. So in this case, 1. Now let's find our second one. So remember, the way we do that is we take the second basis vector and subtract off the projection of the second basis vector onto the first one. So the projection, of course, is taking the dot product of the two vectors and then dividing by the dot product of the one you're projecting onto with itself and then times the one you're projecting onto. So we have the integral from 0 to 1 of 1 times x, and then the integral from 0 to 1 of 1 times 1 times 1. All right. These are not hard integrals to take. You see that you get x minus a half. Also notice here that this number in the denominator is a 1, and this ends up being the square of the magnitude of the vector 1 here, right? Because it's the dot product of the vector with itself, which is the square of the magnitude. All right, let's find the third orthogonal basis vector. So remember, again, we use the third basis vector that we're given, and we project it onto the previous two basis vectors that we have found and subtract it from that third basis vector. So we're getting that orthogonal thing. So here on top is the dot product of 1 with x squared, and then the dot product of 1 with itself. Here is the dot product of the x minus a half with x squared and the x minus a half with itself. A little bit of cleaning up there. We get the x squared minus a third. Now this is a third, certainly on top. It's not a hard computation. If you check, you'll get the integrals here that are both a 12th. And in particular, just for future reference, this is the norm, the magnitude of x minus a half squared, and that turns out to be a 12th. And if you simplify, you get x squared minus x plus a 6th, and I think the 6 is cut off at the bottom of your video, just from what it's looking like here when I'm recording. So this is x squared minus x plus 1/6. The denominator is a 6 there. All right, looking at our fourth basis vector, we need to project the fourth basis vector we're given onto the other three that we've already computed. So this is exactly the same computations that we did before, just using the x cubed as our basis vector in this case, and then the dot products of the x cubed, or the inner products of the x cubed, with each of the previous vectors that we found in our orthogonal basis. Computations for the integrals, I'll leave those for you to check. That one's clearly a fourth. That one's not hard to take. And then we've got 3/40 over a 12th. We already said that this one was a 12th. And again, remember, that's the magnitude of x minus a half squared. This 1/120th is the inner product on top. This 1/180th is, again, the magnitude of the x squared minus x plus a 6th squared. We need those for later. And then if we simplify, we get the x cubed minus 3/2 x squared plus 3/5 x minus a 20th, which tells us now what an orthogonal basis is, not orthonormal. Orthogonal basis are those four vectors. So we've done the hard part. This is like I said, a lot of computations that we needed to do. You could do these integrals on your calculator. You could probably even talk your calculator into changing those into a fraction. Computer algebra systems usually are a little bit better at this. So something like GeoGebra, if you're looking for something for free with a computer algebra system. TI and Spires have computer algebra systems. Some of the ones you can purchase, Maple and Mathematica, are computer algebra systems. Another one that's out there is called Sage. It's free. Anyway, these you can do on your calculator, though, if you just wanted decimal approximations for these. And it certainly wouldn't be hard to tell what the decimal approximations were for 3/2, 3/5, and 1/120th. 1/20th. Yeah. So anyway. All right, so let's normalize. Okay, this is why I was mentioning the things about the magnitude squared. We know that the magnitude of 1 here is 1, not because it's the number 1, but that's because the inner product of 1 with itself is 1. That's important. Don't think that this is 1 just because this was a 1. That's not true. It's the inner product here made it a 1. There are other inner products where the magnitude of 1 won't be 1. The magnitude of x minus a half is the square root of a 12th. That was why I was saying that about the magnitude squared. The magnitude of x squared minus x plus a sixth would be the square root of 1/180th. So the only one we haven't computed is the magnitude of the x cubed minus 3/2 x squared plus 3/5 x minus a 20th. That, again, we can do this way, and that is a wonderful job for a computer algebra system. Get the square root of 1 over 200 or 2800. Then we need to normalize our orthogonal basis. So I need to divide each of these by the magnitudes. So really, I'm going to be multiplying by 1, multiplying by square root of 12, multiplying by square root of 180, multiplying by 2800. And when you do that, you get those numbers that are in front of each of those vectors. So anyway, like I said, I wanted to give you this example just to give you a non-standard inner product on a space to generate an orthonormal basis for that space.